Well, my name is Wei-Liem Loh, and I'm fortunate enough to be a former student of Charles Stein. And since Louis is in the audience, I think he has something to do with it, getting me into Stanford. Right. All right. Thank you, Louis. All right. My talk is in memory of Charles, of course, and Margaret Stein, his wife. And over the years, I get to know Charles and Margaret actually very well. And yeah. Did I get a... That's right. I'm trying to answer that in the next slide, okay? All right. That's the interesting part, all right? Okay. So I get to know them quite well even after I graduated because, I spent at least a few weeks every summer from 1996 to early 2000 at Stanford, thanks to the grant from NUS. So I could travel, and at that time, I don't have any responsibilities, and I get to know them actually very well. I think this is a photo. This is a second photo because Louis showed it in his talk. This is in 2003 when they attended a conference in honor of Charles in NUS. 6 weeks, right? Here, right? So I think the resolution is not as good as your photo, but you can. So this is Margaret and this is Charles, all right? Now, I get to know Margaret actually very well because being overseas, right? The way to contact Charles is through Margaret. I think Louis knows that, right? So usually you write to Margaret and then Margaret will contact Charles. All right, Margaret passed away in September 2016, right? And actually, Charles and Margaret, as far as I know, they're very close. So when I heard that, I was worried that how long can Charles last without Margaret, right? Now, so this is correct. Right. The question is this true? All right. Now, initially, I thought Margaret must be younger than Charles. All right. One reason is well known. I think it's documented in quite a few places that Charles met Margaret when he was a faculty in Berkeley, and Margaret was a student there. Right. So if you think about it, well, a faculty student, one must be older than the other, right? So in 2003, when Margaret and Charles were here, I think during one of the conversations, I sort of said, "Margaret, you look so young." So she said, "No, Charles and I are of the same age." All right? So my conjecture is that it's going to be around 1920, probably MLE 1920, okay? Plus minus one, all right? And so that's the reason why I think maybe they actually shared the same 2 years. All right, okay. Now, the talk is being the last talk of the day, right? It's not going to be terribly mentally taxing. Okay. So what I'm going to do first is to talk about some memories of mine as a graduate student and look at Charles from a personal point of view, not from a researcher point of view. All right. Now, having said that, I remember in the year 2000, right? I think Stanford organized a conference in honor of, and Berkeley, they organized a conference in honor of their emeritus professors. I'm not sure whether Ian remembers, right? There was a conference one day whereby the emeritus, or David, whether you remember, T.L. Lai was the chair at that time, and there was a one-day conference in honor of the emeritus professors of both Berkeley and Stanford, right? So Charles was there with his wife, Margaret. Herbert Solomon was there, but then he was in a wheelchair at that time, and his family came. Lehman was there, Chuck Stone was there, and so many people. And a lot of the past students came. For example, Michael Perman came, and a lot of others. I can't, too many. So it was a really well-attended conference, and TLI sort of asked me to talk something about Charles. All right, a day before. Okay, so I've got to scramble. So what I'm going to talk about Charles from my memories, all right, is something that many of which Charles and Margaret have heard in 2000. All right, and I think they agree in that sense. All right, so there's some verification there. All right, so okay, so let me just try and think about the time that I first met Charles. Right, so it was 35 years ago. time passes, right? So I still remember the day I left Singapore. That's the first time I left Singapore. All right, that's 19th September 1984. All right, the first time you do something, you remember. The nth time you do something, you forget, right? So, I left, and the first time I sort of interacted with Charles is really a luck factor in a sense that I was assigned to be a TA in the first quarter of my first year for Stat 116. Right. Now, Stat 116 is Introduction to Probability at undergraduate level, at the level of Ross. All right. In Singapore, that is our ST 2131. All right. It has a lot of students. And it turns out that Charles was the instructor. Okay. Charles was instructor of Stat 116. Okay. And I mean, he did try to do a very good job, but you know, Charles, those who know him, he kept telling me, oh, he's such a bad teacher, and so forth. So that's my first interaction with him, and there are a lot of students, and there are midterms, there are finals, and Stat 116, the students come after you. Okay, during finals in Stanford Old Sequoia Hall, you can actually see a row of students queuing up to see the TAs as well as the instructors. All right, that's Stat 116. So that's my first interaction with Charles, and it went quite well. I think he's pretty happy with my TA-ship, my grading. Okay, then in the second quarter, the winter quarter, Ian, if you remember, you taught me Stat 233B, that's applied statistics, and you gave a very hard final. Okay. Just an aside, since you are here, right? You gave, probably you don't remember, but we remember as students, right? Students remember more than instructors or teachers. You gave a 3-day take-home final, all right? I have very little sleep during that 3 days. So, yeah, but anyway, it's good training. But having said that, I don't really want to give my students a very intensive take-home final, all right? But having said that, the next quarter, Percy Diaconis taught a class in decision theory, okay? And I sat in on the class. I didn't take it for credit because we are supposed to take the compulsory first-year courses, right? And the notes he used is the notes with Charles Stein, okay? And then I think David said in his talk that he's actually very impressed by the decision theory, right? But he wanted to work on sequential analysis, whereas for me, I think I was very impressed, this is great stuff, I thought at that time. And I think that was a factor that switched me to decision theory, right? I still have the notes, right? Even though it's 35 years old, maybe it's a bit yellowish, but I still have the notes. One other fact is that there's always a little problem if you want to write things with Charles Stein, right? You may not be able to get it published. Like the notes with Charles and Percy. From what I heard, Percy wants to publish it, but Charles' thing is not good enough. Okay, so the notes were never published, right? So I think that's my venture into decision theory, mainly due to Percy's course. All right. Okay. So the third quarter, again, chance steps in. Third quarter in theoretical statistics, there's a compulsory course for PhD students, right? But the third quarter is sort of a free-for-all, sort of without a really set syllabus. And guess who was assigned to teach the third quarter sequence? Charles Stein. Okay, so he was assigned to teach, but he wanted to teach sequential analysis. And the textbook he uses, of course, Abraham Wald's book. And I think that's before David's book, I think, right? I think your book came out in 85 or 86, right? So that was like in spring of 85. That was before your book. So he used that. Now the thing that I remember quite clearly, and I think Charles agreed, all right, during the 2000, was that he tries to be a very good teacher. At least he write down the notes for the first 3 lectures. Right? After that, that's another story. But he actually write down the notes for the first 3 lectures, very diligently. He actually tries. Okay, Another thing that I remember is that when he comes in, he wears a little ribbon, a little red ribbon. Okay. Now, it's not for AIDS, because AIDS wasn't there yet. All right. And the little ribbon is to signify the following. He wants Stanford to divest from South Africa. Because at that time in 85, South Africa was still under minority white rule. All right, so there was a lot of activity on campus in Stanford at that time. And there were a lot of protests, a lot of sit-ins, and he tends to be very active. What he feels very strongly about, he really do it. He's not an armchair guy. He actually does it. So I remember this very clearly. There was one day, we went for his class, we sat in to Sequoia, there's a room in Sequoia Hall, we sat in and wait for him. And guess what happens? Judy Davis, the administrator or the department secretary, we know her very well. She came in and said, well, class is canceled today. Right? Charles has been arrested. so it's quite, at that time for me and fellow students, I mean, it's quite a surprise, right? Like, wow, But of course, I think he was released after a while, all right? He didn't go to jail, all right? He was released, but I mean, that sort of shows that, his intensity, all right, for things that he actually believed in. It's not just academics, all right? He has very strong liberal views, all right? Yeah. Yes. Yeah. So coming back to, for example, Vietnam, this talk is recorded, so I can't really talk too much. Okay. It's recorded. So, but talking about Vietnam, he has very strong views. And for example, he really cannot stand political views. For example, Larry Shepp, for example. Right? Research-wise, it's fine. But politically, Larry Shepp, according to Charles and Margaret, he's for the Vietnam War, which, they really cannot take it. So yeah, actually, that kind of thing. So he is a very active guy, right? Besides, his really famous contributions to statistics, right? I mean, he has the other life, right, which he's actually very active in. He's a liberal. He participates actively in their activities and so forth, right? So I'm not sure how we would think that Trump won, for example, right? But that's another story. So that's one memory that I have. After that, in the summer, I decided to start working on my thesis. So I went to Charles and asked him, "Can I work on decision theory with you?" Okay, and I think Louis sort of asked him many years before, almost the same question, but not on decision theory, on probability theory, right? Now, his answer to me is different from yours. He said, yes, but you must be independent. Okay, you must be independent. And at that time, I don't know what independence is. I'll say yes to anything. Okay, so that's how I started working with him. And I can tell you, his problems are very hard. Like what Hopping said in one of his talks, even the assignments are hard. If the assignments are hard, you just look at the PhD problems it gives you. They're very hard, okay? There are two things that I remember, at least, and I actually tell my students, I have two students here, right, that he tells me, which actually sinks in. One of which is, he says, always look at the simplest non-trivial problem. Okay, and that in some sense is sort of contradictory to our provost's advice. That is, look at real data, make it complicated, right? So Charles' advice to me is always look at the simplest non-trivial problem. The second one, but that's really before the era of computation, right? Before the era of computers, is that's in the 80s, right? So maybe now it doesn't apply that much. That is, don't compute until you have to. In other words, push the theory as much as possible to save on computer time. All right, so that's another thing. I graduated in 1988, and in a sense, it's sort of interesting because I didn't really want to graduate. I was feeling very good in Stanford. So I was just 4 years. I'm going to spend another year, all right? So I went to Charles and said, hey, can I be there for another year? Because nowadays 5 years for PhD is pretty common in statistics, right? But at that time, and Charles says, no, because he wants to retire, okay? So Charles opted for an early retirement because I think at that time, the retirement age is probably 70, right? And he retired age of 68. So he wanted to retire, not because he doesn't want to do research, because he thinks he's not a good teacher and probably shouldn't teach, right? Which is very humble of him in some sense, right? And I think, if you know him, he really means it. He really thinks he's a poor teacher. He's not just saying this, but he really means it. So, yeah, so I graduated in 88, and one more thing about graduation. Many years later, right, when I was during one of the summers, the Steins invited me to their house for dinner, and we were eating. And then Margaret said, why didn't you attend the commencement? I said, and she said, Charles attended the commencement, all right, thinking that you will attend. All right, so, but I didn't know that Charles was planning to attend. He attended the 1988 Stanford commencement, but if I know, I would have gone, all right, because I thought no one is coming, why should I go, all right? I'm not going to pay $100 to rent the graduation gown, right? Right? I mean, especially no one is coming, so I didn't go. So in a sense, I was told later that he did attend the commencement. So in some sense, it's quite caring in that way, all right? Okay, so after I came back to Singapore, that was after my PhD. As I said before, I tend to go to visit Stanford in the summer. I know the place very well. Stanford is very kind. I have a sort of shared office and so forth. So it's actually quite nice and you can talk to people like Art Owen and all that, and Charles Stein. So I went there quite a few summers, all the way to maybe early 2000. So for this period of maybe 7 years, all right. That's another aspect of Charles that I think some people know, but others don't. He is a really enthusiastic hiker. Right? He's a serious hiker. Even when I was a student in the 80s, right, when he comes in, he used to wear running shoes. Right? It's not the usual leather shoes. He wear running shoes, and I'm not really an exercise freak, right? So I don't. But my classmates all tell me that in the evenings, Charles will actually run along the Stanford track. So he really he exercises seriously, right? And he likes to hike. He was a member of the Sierra Club, which is a sort of naturalist club, and he joined them for hikes. And the hikes that he takes are pretty long, right? He sort of told me that the average distance is 17 miles. All right, 17 miles is quite a distance, right? And he likes to hike at night. So I don't follow him at night, but he likes to hike at night, not alone, but as a group from the Sierra Club, right? I think they organize, and he goes for hikes, which is a very healthy thing. That's why it's so slim, I think, all right? So there was once, I think in 1999, I was there for the summer, and then he asked me, would you like to go for a hike? Okay, you can't say no to Charles, right? Even though I said, okay, so I said yes, and I think it was a Sunday, and this is the first time I saw him drive. I've never seen him ride a bicycle. I've never seen him drive until that day. All the time he walks, right? He walks all the time. So on that day, on Sunday, for the hike, he actually drove his old Volvo. I was staying in a motel and he drove, and I got on and he got all the spare water and all that. He's a professional, so he got all the water that he needs. And I think we went to some park in the foothills. All right. So he said, let's walk, right? Let's hike. So I think the total distance that we hiked was 8 miles. He said, that's a short hike, Let's do 8 miles. And after 4 miles, he looked at me and said, are you okay? you know. Because I haven't hiked before, you know. So, well, that was my experience, all right. So he really likes hiking exercises, besides his well-known academic achievements. When he was here in 2003, he also asked me, he wants to go and hike, okay, in Singapore. So what happens, that was in August. It's quite hot in August, right? But nonetheless, okay, we go, and I grabbed Anthony Cook. So both of us, Anthony Cook and myself. Anthony Cook was a student at Stanford also, so he knows Charles. Anthony Cook used to say that when Charles teach him a course, he's the blackboard cleaner. He clean. All right, so both of us actually took him up, accompanied him to Bukit Timah Hill. All right, so he actually hiked up Bukit Timah Hill and then back. All right, no problems. All right, and he was actually quite happy. All right, so these are different aspects of Charles Stein that is not really documented too much, right? You have to dig before you can find something. So that's my memories of him, and they are very good memories, right? Okay, so that much for these things, and a lot of it actually I talked about in the 2000 workshop or conference. The only difference is that in the 2000 workshop, in honor of all the Professor Emeriti, because there are so many at that time from Berkeley and Stanford, each of us were given like 7 minutes. If you stretch it, at most 10 minutes, right? So I have to compress everything into 7 to 10 minutes. Now I've got more time. All right, so, okay. So these are the students of Charles Stein, and I got it from Math Genealogy, all right? And I think they are reasonably complete. So his first student is 1958, and I'm the last one, I think, 1988. So there's a 30-year span. What is of course, Louis is here in 1972. And what strikes me among this list of students is that among all these students, only Louis does probability, right? And all of us are in decision theory, I think, right? And there was an interview with Charles in the institute here. They call it imprints, and Leong Yu Kiang, the person who interviewed him, asked him what contributions does he think? What's his best contributions, right? And I think his reply was probability, Stein's method. Right, so that's actually quite interesting. So probably Louis might have something to do with it, because the only student of his who does probability for his PhD. All right, okay. All right, before that, let me just go down a little bit to I think since 2005, I think Anirban Dasgupta from Purdue actually encouraged me to put together Charles Stein's bibliography of Charles Stein. And one of the motivation really is that he has a lot of unpublished work, and if we can get it online, that will be very good. All right. So in a way, I've actually put down, as far as I know, he has like 40 publications. 40 published works, and if any, and Ian actually suggested just 1 or 2 days ago is to actually put this online so that it can be retrieved by people easily, all right? Which is an excellent idea. So maybe you have to think about where to actually put it so that it can be accessed easily by Google or something like that. Now I've also checked the Math Science Net. All right, the Math Science Net under Charles Stein is actually reasonably complete. It has actually 36 publications. There are 2 publications that are missing from the Math Science Net, one of which is his econometrica paper, which over here, right? So number 5 is missing from Math Science Net, and the other one that's missing from Math Science Net, which I'll say a little bit more later on covariance matrix estimation, is his 1986 paper, which is published in Journal of Mathematical Science, this one. Okay, so these are 2 papers that are missing from the Math Science Net. Other than that, I think you can get things from the Math Science Net. If any of you can come up with any other publications, just let me know so that I can just add it in, right? So that we can actually put it somewhere on a site where people can at least get easily, right? Okay. Okay, let me see whether I can. Right. Okay. Now I've got to speed up a little bit because I plan to finish by 3 and I'll try and do it in 20 minutes. Okay, I think this is unnecessary. Just a brief summary of Charles Stein. And since this is the last talk this week, I don't really need to go through these contributions of Charles. For the first one, this is actually his first published work. It was done during the Second World War, I believe when he was in the Air Force, right? There's at least one story about this paper that maybe I want to share. That is that the question is, why did Charles go to Columbia University to do his PhD? Okay, I mean, he could have gone anywhere else, and he did his undergraduate in Chicago, so why did he actually go to Columbia? According to Charles, he said that he went there because Columbia agrees that this paper can be used for his PhD thesis. So he doesn't need to write a new PhD thesis, he just needs to go there and fulfill the requirements, other requirements. So I think he actually got his PhD in 1 year or something like that. All right, so that's one story, which is very deserving because this is actually an excellent paper. You know, any PhD thesis, this is really a good PhD thesis. All right, not many PhD theses can have this. All right, this kind of fame. All right, so he has actually lots of contributions academically, and I've just written out some of them. But I think Louis mentioned the Stein theorem, and he didn't publish it because he thinks he can do better. All right, but he never got around to finishing it. So, who is Hunt? Is Jeff Hunt, and Jeff Hunt eventually became a faculty in Princeton University mathematics. All right, and both of them were in the Air Force in the same base during the Second World War. All right, and that is admissibility, Stein paradox, and there's a lot of talk about it, so I don't really need to. These are next week will be on Stein's method, 1 whole week of it, all right, and so forth. So Charles has many contributions, and I'm sure it will stand the test of time, right? All right, so let me just talk a little bit about covariance matrix estimation, and that's really my thesis topic, and so it's rather close to me. I'm going to describe some of Charles' work on covariance matrix estimation. Now, the first well-known work is in 1961 in the 4th Berkeley Symposium. This is a paper that shares the limelight with the James Stein estimator, and because of that, I think this result is sort of slightly overlooked because of the prominence of the James Stein estimator. But this is actually a very interesting stuff. Charles is an expert on invariance. All right. A lot. I think my belief is that the origin, the first time he derived the James Stein estimator, is really through invariance. But after that, there's lots of ways of doing that. But I think so this is the 1961 covariance estimator of Charles. And this is just the setting. This is the data matrix. Let's assume that it's Wishart with dimension P, and this is the population covariance matrix, and this is the degrees of freedom. In a way, you can think of it as somewhat sample size. And he took this loss function, and now this loss function is very well known. Some people call it Kullback-Leibniz loss. Some people call it entropy loss, but most people call it now Stein's loss in honor of Stein. All right. And what he did is actually to construct a very nice estimator, a very beautiful estimator for sigma. Okay, sigma doesn't need to be diagonal. All right, sigma is just an arbitrary positive definite matrix. And it has a remarkably simple expression, which is very nice, like the James Stein. It is constant risk minimax, right? And it dominates any constant multiple of S, including the sample covariance matrix. All right, so what's the estimator? All right, this is the estimator. And to construct the estimator, well, this is the data. This is the, which has a Wishart distribution. And you do the Cholesky decomposition, that's all. So these are upper triangular matrices, T prime times T, right? And of course, in between these two guys, you can put the identity matrix, right? It doesn't change anything. And what Charles does is he actually shrinks the identity matrix in between, and you get something like this. Right? And this reminds me of a talk previously whereby, I think Matsuda, you sort of said in Charles' 1974 paper, he shrinks by -2i. Remember that? So there's this -2i coming in here also. All right? I mean, there's some relationship, I think. All right? So this is a very pretty estimator. It's probably as simple as you can dream it to be, right? Closed form. But of course, Charles noted that this is still no good, even though it's pretty, because it's still inadmissible and it has an appealing feature of being invariant under permutation. So it depends on which variable you arrange first, right? But this is a very nice result. And this is really available in textbooks now. So if you look at Anderson's multivariate analysis or Moorhead's aspect of multivariate analysis is there, all right? So this is actually a very nice feature. But Charles is not happy with that because it's not good enough, all right, in terms of performance. Okay, so so that's where the Wishart identity comes in. Stein's lemma. There are many Stein's lemma around. One on sequential analysis, one on decision theory. So the Stein's lemma is in decision theory. Sometimes it's related to the normal identity, all right. But besides that, there are other identities. So we have something called the Wishart identity. So since the 1950s, Charles observed that the eigenvalue, this is something that is quite easy to understand, that the sample eigenvalues of a sample covariance matrix are much more spread out. All right, and that's quite easy to believe, all right? And his idea is, well, if you can improve on the dispersion of the sample covariance matrix, you should do better. All right, you should do better. So, so he started doing that in the 70s or maybe even the 60s, I don't know. But at least by 1975, he gave a Rees lecture, okay, in which actually he developed a calculus of eigenstructure from scratch for the Wishart distribution. All right, it's a calculus of eigen. It's I've got the notes, but he, of course, is well known. He never published it. Okay, it was never published, and it's a very beautiful and very elementary approach to study the eigenvalue structure of covariance matrices or the Wishart matrix, right? And the bottom line is that under suitable, really weak regularity conditions, he has this identity, which is what we call the Wishart identity, because S has the Wishart distribution, right? And this exact is not an approximation, and this, of course, what Stein does usually is through using partial derivatives, right? So this is actually a partial derivative operator, right? Okay, so he got this in the Rees lecture, right? But he never published it because he was trying to get an estimator, not just the Wishart identity. Okay, the story is that from what I heard from Charles is that Len Half, all right, he's I think retired and he is in UC San Diego, I think, yeah. In 1978, he also independently proved this Wishart identity, all right, independent of Charles. But of course, Charles got it a few years earlier, right? And from what I heard, Leonard has a shock because he gave a talk in Stanford on this, right, in around 1978 or even 77, and he found out that Charles has got everything. Okay, and for a young guy, that's devastating, right? I mean, you work so hard, But Charles is actually very nice. Charles is not going to publish this, all right? So actually, Half actually published a lot of it on the Wishart identity, as you can see from the website.net, right? So I met Len Half in the 80s when he visited Charles, and very nice person. So this is actually the story, but the proof is actually very different. Len Half's proof and Charles' proof is actually very different. Len Half's proof uses multivariable calculus using Stokes' theorem, Green's theorem, and so forth, right? Whereas I think Charles is actually more elementary, right? Which is actually nice, right? Okay. Now, that leads us to Stein's 1975 covariance matrix estimator, all right? So keep in mind that what Charles wants is to shrink the eigenvalues, right, in the best possible manner to get the savings in risk. So he considers the orthogonally invariant estimators of this kind. All right, and this the L is the diagonal matrix ordered suitably, so that is definite. All right, and this R is actually the orthogonal matrix, right, that you can diagonalize S. Right, and this is the unknown that you want to find, right, and assume that this is a diagonal matrix. Okay, so this is the orthogonally invariant matrix. Now, with his calculus of eigenstructure, right, and using Stein's laws, and after some work, which I'm not going to talk about, he works out the Stein's unbiased estimate of risk, right, for this estimator. Right, so phi is the unknown, right? But there are actually more than one phi. There are actually p phis along that diagonal, right? So we have got this. Now, one use of this Stein's unbiased estimate of risk is the following. If you have two estimators, you know the two phis, then you plug it in and see which one is bigger, right? Okay, so that's one way. But what Charles wants is sort of, he wants more. He wants this expression to tell him which phi to choose, all right, rather than to come up with a phi and check, all right? But here's the problem, right? You can rewrite this in this way if you just use this transformation. So the problem here is that this expression, the terms without the size, you can ignore because you're trying to minimize the size, so it doesn't matter. These are essentially constants without the problem of minimizing the size as it stands is not possible because there's this derivative, right? I mean, it's possible, it's impossible, I think. So, and this expression appeared in Charles's Rees lecture, and what he did is something I don't quite understand. In the following, it's like a leap of faith, and that was done in 1975 without really fast computers, right? So how does he know? I mean, so what he does is the following. He ignored the partial derivative, right? He just ignored this. And if you ignore this, of course, you can minimize psi, right? Okay, just differentiate with respect to psi and just solve it, right? And that's what he does. And if you do that, then the minimization of this expression here, without this term, right, just these two terms, would be the following. Okay, so this is his first approximation for the diagonal elements of his orthogonally invariant covariance matrix. But as he observed, because of this approximation, you leave this term out. There will be cases whereby the ordering is violated. Right? The ordering meaning that if you look at this, there's this ordering. So 1 is bigger than 2 is bigger than 3, right? So if you just use this ad hoc approximation, just ignore this and just minimize, the ordering may be violated, especially when the eigenvalues are close together, right? I mean, so what Charles suggested was, so for example, he knows that this may not be true and this should be true, right, if it's a legit estimator. So Charles proposed an isotonic regression to modify these size, all right, isotonic regression. So again, it's some sort of ad hoc. And if you do that, then you get Charles' 1975 covariance matrix estimator, all right? So that's it. And again, he did not publish it, right? Mainly because he thinks that he can do better, but it's not published. Now, as a student, actually, I did a lot of simulations. At that time, the computer is actually very slow, and I spent the nights in the computer, the mainframe, they call it Sweet Hall. I was there, staying most of the night trying to get it to run. And I'm doing only dimension 10. Okay, p equals to 10. I was spending a whole night getting it to run. So that, but the performance of this estimator is actually excellent. There are a lot of competing covariance matrix estimators at that time, all right? But actually this one is actually quite outstanding. Even though you think about it, it's rather ad hoc, but it's quite outstanding. So it reduces the risk drastically when the eigenvalues of sigma are close together. It is almost minimax, it's slightly above minimax when the population eigenvalues are extremely far apart, right? But it's only slightly. At that time, I think in decision theory, minimax and still is a big thing, right? So you really want the estimator to be minimax if possible, right? And even up to today, Stein's 1975 estimator has been called by many as the gold standard that you want to compare with, right? It's a gold standard. So now here's some story. So Charles' 1975 Rees lectures were unpublished. In 1977, Charles was invited to Russia, Leningrad, right, to give a series of lectures on estimation, of which the covariance matrix was part of his lectures. All right, the covariance matrix work were part of his lectures. The catch is that Charles has to give the lectures in Russian. All right, but actually at that time, Charles knows Russian, including his wife. His wife knows Russian to the extent that she was, for many years, the translator for the American Mathematical Society of Russian papers into English. So actually Charles, but now, many years back, I asked him, I've forgotten Russian, but at that time he knows. So he actually delivered it in Russian. So the notes were written in English, translated to Russian. Okay, yeah. So that he can give it in Russian, all right? So when I was a student in the 80s, I sort of asked Charles, can I have those notes, Can I have those notes? Because, they're not published, right? And they're Russian. I don't know Russian, So he said, well, he lost them, He lost the original English version. I don't know where he put them. It's lost, all right? And he also told me that they actually translated the Russian back to English, but he misplaced it anyway. Okay, so I was actually quite depressed in a sense, or quite sorry in a sense that these are actually very nice notes. It's actually his work on eigenvalue structure, right? Calculus eigenvalue structure. If you don't get this, they might be lost for good. All right. So for many years, I was actually, and with the encouragement from Anirban Dasgupta from Purdue, I was trying to actually get hold of these notes and so forth. And I asked Jim Berger, I asked Percy Diaconis, I asked Larry Brown. I think Ian, I probably asked you also, but no, you couldn't get any. So, but luckily, just a few years back, I think maybe 2011, somehow I stumbled upon, and someone found this publication, which is listed down in the bibliography, right? It's in the Journal of Mathematical Science, 1986. And it's published, so at least there's documentation, right, which is quite good, right, in the sense that if people are interested in his work, they have access to it, right? It's open. Now, here's a final footnote. Charles never mentioned this publication to me, right? When I was a student, it seems that he doesn't know it existed, right? And even in the early 2000s, when we are actually trying to look for all his unpublished papers, he sort of never indicated to me. So there's a chance that either Charles forgot about this publication, or he's not aware of this publication at all, okay? Even though it's published under his name, all right? But actually, it's really fortunate that it is there, all right? So at least it's documented, all right? Now, actually, I've reached 4 o'clock. So maybe if I can take 5 more minutes, and then I'll stop. All right. Actually, I can go on, but it's probably not polite to go on. So covariance matrix estimation now and then, right? So in the 80s, the computers are pretty slow, and I was working on my PhD thesis. We are looking at p equals to 10, right? And already that's sort of stretching things, So nowadays, life is much better. The computer is extremely fast. So the covariance matrix estimation problem that Charles was interested in is decision theoretic in nature, in particular, finite p and n bigger than p, right? And that's probably the best we can do at that time. And we are actually considering p equals to 10 to 50, something of that order of magnitude, right? But in 1990s, due to the advancement of modern computers, as you know, we are interested in high dimension p, low sample size n, so things are different, and n can be much smaller than p, right? So the dominant technique, at least from what I know, which I'm not an expert, is random matrix theory. It's becoming increasingly important, and in particular the Stieltjes transform and the Masenko partial equation. So these are techniques that I think people use more often now. So here are some recent spectrum. I'm just going with the literature. They're actually doing spectrum estimation instead of covariance matrix estimation. But if you are doing orthogonally invariant covariance estimators, then of course the spectrum estimation comes in, right? So with the rest of the time, the last few minutes, just highlight, these are the three promising, at least to me, covariance matrix estimators, I would call it the hypermodern ones, okay, the modern ones, that I think are very promising, and they work for n bigger than p, n smaller than p, and so forth. Now the first is due to Nuruddin Al-Karol, who was a student of Ian, right? And David, okay, and David, okay. So here's this estimator for the spectrum, and I think it's a very nice work because he uses the Masenko partial equation. I mean, when I look at the Masenko equation, it's so complicated, but he managed to see it and turn it into a convex optimization problem, and that I think is the key, right? The nice thing. Okay, so that's a good point. What's the not so good point? The not so good point is that he doesn't give out his code. Okay, so you have to write your own code. But people write different codes, so he doesn't have a code online that you can use to check, right? The other one is Loh and Wolf. They have a series of papers, and probably more than this, and what they do is, again, the Masenko partial equation, but what they do is they extended the Masenko partial equation to incorporate sample eigenvectors as well. So in that sense, they have a little bit more mileage, and they could actually get a very decent and estimated. And the last one is Kong and Wei-Liem. I think these two guys are from Stanford, I think, maybe computer science. And they use method of moments. All right. So I'm going to have 3 more slides. No, maybe 4 more slides. Okay. So I'm going to compare these 3 estimators of theirs to the Stein estimator, 1975 Stein estimator. All right. And this is a loss function. You can use other loss functions you like. All right. But this seems to be the one that these guys actually are interested in, so we just follow them, all right? Okay, so these are the eigenvalues, these are estimated eigenvalues, and they are ordered, the I are ordered, and these are the population eigenvalues, the I's are ordered, all right? So that it makes sense, all right? So these are simulations, and this is done by my former student Jun Wen, who I think is here somewhere, right? Okay, so let me just report then I've got 3 simulations. There are lots more, but this is representative. This is a Stein estimator, this is P, right? And N is 3P. So if you know P, you know N, because N is 3P, right? And this is the Wishart, and this is the identity matrix. So all the eigenvalues are the same, population eigenvalues, and for P equals to 10, 20, 30, this is a Stein estimate, and this is done in 1975, and this is the Loh and Wolf, this is Al-Karol, and this is Kong and Wei-Liem, right? And the Stein estimator seems to be pretty competitive. It's not that bad, right? Even though it's 30 years older than the 3 current ones. But it loses out in, well, it's still okay, at least for the identity, right? So, and it seems that this Kong and Wei-Liem seems to string a lot, but usually when you string a lot, it sort of tells you overstring. So you lose somewhere, right? You do lose somewhere. So that's the first slide. The next one, I think June, my students sort of spread it out a little bit, the eigenvalues, population eigenvalues, and you got something like this. This is a Stein estimator. Again, when P is between 10 and 50, it's actually comparable. I mean, you can fight, okay? But of course, when you go big, like P equals 1,000, I think Loh and Wolf does better, etc. Right? They seem to do better. And finally, when they're not that far apart, when they are in order 1, 2, 3, 4 until P, this is when they are sort of spread out. Then you have the Stein estimator, the Loh and Wolf. Now, if you look at Kong and Wei-Liem, they actually do quite poorly, right? When the eigenvalues are spread out, mainly because of the method of moments, which is actually not very accurate for high order moments. So that's maybe one reason. But Loh and Wolf seems to do better. But my point is that when P is between 10 and 50 and N bigger than P, the Stein estimate is not that bad. All right? It's still competitive. All right. So I think I've taken more than enough time. Thank you very much. Even though I have more, but I'm going to stop here. All right, thank you.
Thanks, Wei-Liem, for the interesting and I think very talk.
Thank you. It's hard to find questions on this. I think, yes, actually, but not very successfully. I think you're talking about Stein estimator, 1970. The theoretical analyses, I think all the later competitors, they are sort of consistent in a weak sense, right? I mean, like Al Carroll's estimator is consistent in a weak sense that the empirical spectrum that converges weakly to the population spectrum. I mean, so there's actually theoretical analyses for these, the hypermodern three estimators, but the comparison, no. All right, but there are lots of possibilities in a sense, right? But for the Stein estimator, it's because of the unbiased estimate of risk. I think it's actually quite hard. There's one paper that I know by Bala Rajaratnam and his collaborators, but I think they work out p equals to 2, right? Which is not that interesting, right? I mean, you want p to be bigger than 2, right? But I'm not aware of course, Lenhardt has more work on this. Lenhardt actually got this too because he got the Wishart identity, if you recall, right? So he actually did another version. Instead of leaving this out, he does what he called a variational Bayes method. His paper has an interesting history, right? I first saw his Lenhardt's report on this, on variational Bayes, another way of getting an estimate. It's very similar to Stein's estimator, but he used some sort of Bayesian method. But in terms of performance, almost the same, right? I saw his technical report of his in 1984. Okay, that's half. He's a very nice guy. So he gave me a technical report, and it's very readable. Okay, and you know what year it was published? 1991. Okay, that was like 7 years. Okay. So at one time, I was in Purdue. I was talking to Jim Berger about this. Wow, it's so long. And Jim Berger said, well, he was the AE handling it. Okay, and he says, don't blame him. He never submitted the revision. So it reminds me of Lewis, who had it for 18 years and didn't submit a revision. So yeah. So I think Half has done some work, but it's sort of different, But it's not really a theoretical analysis. It's a way of bypassing the isotonic regression, right? By using the Euler-Lagrange's method and sort of maximizing it. So yeah. All right, thank you.